7. All right, just to summarize then, a single molecule of this on average weighs 44.01 U. In nature, are you ever going to find a CO2 molecule that weighs this amount? No. If I had 602 million trillion of these molecules, what would the total mass be? 44.01 grams. Right? And so 602 million trillion is some kind of magic number. 44.01 grams. All right, so let's go back to ammonium nitrate here. We did this, and so what do we say? We say it's 80.06 U per. Since it doesn't form molecules, we use the generic term formula units. We could have done the same thing with CO2 here. This formula units is used for everything. And so this could be 44.01 U per formula unit of CO2, formula unit being one molecule. However, there was a distinction between empirical and molecular, which we talked about with hydrogen peroxide a while back. That's what molecular is still. We wouldn't want to call everything. You might go, well, why don't we call everything formula unit? Actually, we could. But could we call everything a empirical unit? No, we can't. The formula unit for ionic compounds is always the empirical unit. The formula unit for molecular compound is not always the empirical unit. Okay, so we did ammonium nitrate. It's an ionic compound. They did something bizarre here. What are they doing here? They're creating extra work, I think. Yeah, and so if we look at nitrogen, that's fine, 1401. But here, yes, okay, it's going to be more precise because the more digits we have, the more precise it is. But at what cost? The cost is going to be speed, because now you have to do extra step. What extra step do you have? You have to do a rounding step. Whereas if this were just 101, then we wouldn't have to deal with a rounding step here. And so normally I would just leave it at 101. It's going to be 404. But what did they do here? There's something terribly wrong. They've taken 3 oxygens at 16.00. They're getting 48. And this is not correct. This looks like 2 sig figs. In other words, no decimal places, so we'd end up with 2 sig figs in our final answer. But this is wrong. It should be 48.00. So I don't like this at all. If I saw this on a test, I'd think it's wrong. I'd mark it off wrong. And deduct. Well, apparently they must have meant 00 because they end up rounding it here. And then do one more round off somewhere here. I'm a little off though. I came out to 80.06 because of round off error in hydrogen. But I'm willing to sacrifice that loss of accuracy, the small loss of accuracy for speed. Because these are such common elements that we can calculate the molar masses quickly in our heads versus carrying extra digits. Only time you would use hydrogen as 108 is for the 2 cases. I would use hydrogen for 108 if I'm talking about atoms of hydrogen. How much does an average atom of hydrogen weigh? It weighs 108. And that gives me 4 sig figs. I want 4 sig figs in my calculations usually. Or if I'm talking about H2, if I use H2, I could do it 2 ways. I could say, oh, it's 202 U per molecule of H2. Or I could say it's going to be 2016, 108 times 2, 108 times 2, 2016 U per molecule. And so in this case, I wouldn't use the 101 because I would end up with 3 sig figs. Here, again, I wouldn't use 101 U per atom because I'd only end up with 3 sig figs. 4 sig figs, the typical conversion factor. All right, so let's talk about where this number comes from here. This 602 million trillion, and it's not magic. It was just really crafty way of defining this relationship such that the numbers work out like magic. And so what is it? Where did the 602 million trillion come from? So let's talk about that. When we read this, it's a little bit confusing because it says amount of any substance that contains the same number of units as the number of atoms in carbon-12 in 12 grams of carbon-12. And so this is a little bit confusing, I think. So the definition or the origin of this number, and this is the number we're going to memorize because, you know, usually when we have numbers like this, we like to use how many sig figs? Usually when we're doing calculations, we like to have 4 sig figs, our conversion factors. And so this one we're going to do to 4 sig figs. It's going to be 6.022. Now this is exact, no it's not exact, there are more digits after this, but we're going to stop at 4 sig figs. So I'd like you to memorize this as 4 sig figs, 6.022 times 10 to the 23rd, not 3 sig figs, 6.02 times 10 to the 23rd. And it's not hard to remember this in 4 sig figs because it's 6.022. Just add another 2. And this is going to help us with our calculations. So what's the origin of this number? Now, for some numbers, we don't care about the origin. It's fine, like the dozen, you know. How come a dozen? You know, a dozen donuts, 12 donuts, 1 out of 10. Well, it's okay, we can use it, and we won't worry about it. But this number we have to worry about because, you know, what if I want this number to 10 sig figs? You know, then would I have to know where it came from? You know, how did they come up with this number?
Wasn't it like some guy was going to get a loaf of bread every morning? I sort of told me how they got done.
Oh, every morning the guy went to get a loaf of bread?
No, it's like donuts or bagels.
Oh, okay.
People lab and like 12 every time.
12 every time?
Yeah.
Oh, so it's due to one customer always ordering 12.
Yeah.
Oh, that makes sense. And so what you have to do is you have to develop a story for this number. This number we call the mole. And the number specifically is called Avogadro's number. Avogadro. Avogadro's number is abbreviated M sub A. The mole is abbreviated, you know what the mole? M-O-L. So it's not such a great abbreviation. The mole, abbreviated M-O-L. But this is good though. Avogadro's number, or Avogadro's constant, abbreviated N sub A. And so where did this come from? Well, the way this was defined is like this. What we're going to do is we're going to take exactly, now how can you weigh out exactly? So this is kind of a thought experiment. If we got exactly 12 grams of carbon-12, so this is pure carbon-12, there's no carbon-13, there's no carbon-14, just pure carbon-12. So if we get exactly 12 grams of carbon-12, it consists of a lot of atoms of carbon-12. And then what we're going to do is we're going to count the number. We aren't literally going to count them like 1, 2, 3, 4. We're going to calculate them, but essentially it's count the number of carbon-12 atoms. There's another word that's used sometimes instead of saying carbon-12. Since it refers to a specific isotope, we could use the other word. Do you know the other word for that? An atom of a specific isotope? It's called. Starts with an N. It's called a nuclide. So if we count the number of carbon-12 nuclides in here, then this is what we get. There are approximately 6.022 times 10 to the 23rd carbon-12 atoms, or nuclides. And so that's where the number comes from. If we look at Avogadro's, well, there are a lot of carbon-12 atoms in there. So let's take a look at Avogadro's number to more sig figs. Well, here's it to more sig figs. So we aren't going to use that many sig figs. Actually, there's more sig figs than that, even. So, look at the maximum number. Maybe that's it. So go through 10, okay. All right, so here we see 6.022, et cetera, et cetera. What we're going to do is just 4 sig figs, 6.022 times 10 to the 23rd, 4 significant figures. All right, so what this is going to do is going to mean that this number relationship holds. So the number relationship, just repeat that here. Goes like this. So what's the average mass of a carbon atom? So there's going to be 12.01 grams of carbon atoms. The average mass is 12.01 U. So we have 12.01 U of carbon atoms per carbon atom. Actually, this doesn't quite make sense. Let me just restate it. It's 12.01 U's worth of mass per carbon atom. That makes more sense. Here, this would be 12.01 grams per mole of carbon atoms. And how many atoms are there in a mole? Yeah, so it would be 12.01 grams per 6.022 times 10 to the 23rd carbon atoms. The average water molecule weighs 18.02 U per H2O molecule. Well, that means because of the number relationship that we set over there, that means 18.02 grams would be the mass of how many water molecules? A mole of water molecules. How many water molecules in a mole? 6.022 times 10% to the 23rd. There are 80.0, what did I get? 80.06 or 80.05? 06. 80.06 U per ammonium nitrate, what? Per ammonium nitrate. Does ammonium nitrate form molecules? No, formula units. A formula unit of ammonium nitrate consists of one ammonium ion and one nitrate ion. Or there would be 80.06 grams per mole of ammonium nitrate, what? Formula units. In other words, that would be the same as 80.06 grams per 602 million trillion ammonium nitrate formula units. And so this is the number relationship that we get when we define this in this way. And so we get a mole, which is an Avogadro's number's worth of units. Like a dozen is 12 units. All right, next we're going to try out some calculations with this. Let's say I have a quarter mole of ammonia. If I have a quarter mole of ammonia, how many ammonia molecules is this? Ammonia is a molecular compound. So first, what is the formula for ammonia? NH3. And so I have 0.25 moles. The way we solve these type of problems is we do dimensional analysis. But 0.25 moles of ammonia, and then I look for something that can cancel out moles of ammonia, and this is moles of ammonia molecules. It's a bit of a hassle writing molecules here, so sometimes we'll just leave it as moles of ammonia. But what we're really talking about is moles of ammonia molecules, or in other words, 602 million trillion ammonia molecules. And so we're looking for something that cancels out moles, or moles of ammonia. Well, we have something that cancels out moles. And a mole is just like a counting unit. If this were a dozen, then we put 12 units here. If this is a mole, how many units are we going to put here? 6.022 times 10 to the 23rd units. And so one mole is equivalent to 6.022 times 10 to the 23rd molecules, or whatever units we have. Well, the units we have are ammonia molecules. So moles cancel. That leaves us with 1/4 of that ammonia molecules, and then let's see what that comes out to. .022. So I get one. How many sig figs am I allowed here? 2. And so the reason why I want 4 here is because often we're given 3. We're given 3 here to minimize round off error. We want to have more here. If I'm given 2, then this is plenty, more than enough. 3 would be adequate. But if I'm given 3 here, I want 4 here. If I'm given 4 here, I want 5 here. If I'm given 6 here, I want 7 here. And that's just to cut down on round off error. But you know, we don't want to memorize a whole bunch of different numbers, so we're just going to stick with 4 because 4 is going to be the most versatile. And so we'll round this to 2 sig figs. It's going to come out to 1.50 times 10 to the 23rd molecules of ammonia. So just NH3 molecules. So we could read this as 150. This would be 150 million trillion water mole ammonia molecules. There's a quarter mole. So let's take a look at their solution. The one thing you notice right off is we used 4 sig figs here, they used 3. 3 would have been okay here in this particular problem. In other problems, it would have been as good as 4. Okay, and then they end up with, well, is this the correct number of sig figs? No. So there's some change here. Now, when we went from chapter 6 down to chapter 7, they have a different person making the slides. Because I could never get them to carry extra digits, right? They would just round it immediately. On all the previous slides, I didn't like that. I wanted them to carry extra digits and then round it in the next step, right? And so we were allowed 2 sig figs. This would round to 1.5. But if I go to the next step, there is no next step. They just left the answer like that. So it's wrong. So there is a different person working on this. The first person was crazy about rounding. This person doesn't even care about rounding. This one. The same thing with the answer keys. You know, you have different people working on the answer keys. You see this all the time. It drives you crazy. consistent. All right, then we have something called the molar mass. The molar mass is what I've been talking about, and that's a relationship here. It's tricky to see in this particular case. And so, for example, we know that there's exactly 12 U for each carbon-12 atom. What do we call this mass? This mass is called the atomic mass, but sometimes it's confused because do we mean the average atomic mass or just the atomic mass? Just the atomic. This is not an average because we're only looking at one isotope. And so to clear this up, sometimes instead of calling this atomic mass, I'm going to call this the isotopic mass. To be a little bit clearer, because this is the mass of a specific isotope. Isotopic mass. And so in other words, we have 12 U's worth of mass for every carbon-12 atom. Because of the mole relationship, this could be translated to there are exactly 12 grams in a mole of carbon-12 atoms. Now, what do we call this? What we're going to call this is the molar mass. Molar mass. And so atomic or isotopic masses, those are going to have U per atom or isotope. Molar mass is going to be grams per mole of atoms. Or, I shouldn't call it isotope. I should call it, there's another word, the word that we get to the end, which is what? Euclids. Euclids. Go ahead and start with that. Now this is something that gets confused all the time. If I look at CO2, an average CO2 molecule weighs 4401 U. This is for a CO2 molecule. And so what should I call this? I should call this the what? Well, atomic mass would, if I just had a single atom, but this is not a single atom. This is one carbon and two oxygens put together. What would we call this? Yeah, molecular mass. We're going to call this molecular. The molecular mass is the mass of an individual molecule. Molecular mass. I could also call this the. I could call this molecular mass, or I could call this the. This is the average molecular mass. I'm leaving off average here. It's the average. So I'm not looking at specific isotopes. And so this is the molecular mass or the formula mass. Which happens to be the same as the empirical mass. The empirical mass, what was the empirical formula again? The empirical formula was the simplest whole number ratio. And so CO2 actually occurs as a molecule and the empirical unit, which is the simplest unit, or simplest unit ratio. All right, well, because of the way the mole is defined, I can say 44.01 grams per what? Per mole of CO2 molecules. And so what should I call this? I should call this the molar mass as well. The molar mass. The molar mass is just defined as the mass of a mole of units. It doesn't matter if the units are atoms. It doesn't matter if the units are molecules. And it doesn't matter if the units are what did we call this? Ammonium nitrate. Ammonium nitrate forming the units, yeah. And so this, what would we call this here? We call that the molecular mass? We would call it the atomic mass? What would we call it? Well, we wouldn't call it the molecular mass because ammonium nitrate does not form molecules. We wouldn't call it the atomic mass because we're not dealing with single atoms. Therefore, what do you guess we're going to call this? Formula mass. That's what it's called. This is called the formula mass. So this would be the mass of an individual formula unit, formula mass. And it's going to be U per formula unit. U per formula unit. Okay, what would we call this? 80.06 grams per mole of ammonium nitrate formula units. What would we call that? We would call this the molar mass. And so regardless of what the unit is, we use molar mass to do everything, you know, where we have the units grams per mole units. Okay, so let's just get some practice. Calculate the mass of calcium fluoride. Well, what mass do they want? Well, I guess it doesn't matter, so we're just going to calculate one of them. And so the first thing is we need the formula for calcium fluoride. What is the formula for calcium fluoride? CaF2, good. That's because we know calcium is 2 plus, fluoride is minus. Is this an ionic compound, molecular compound, covalent? No. This is ionic. And so do we expect molecules or? No. All right, so calcium, I don't know the number of calcium. So let's take a look at the periodic table. So calcium is in the second column. The first column we call the alkali metals. This is the first family of elements. They all have somewhat similar properties. As do the second. The second family is called the alkaline earths. So calcium, magnesium. Similar properties there. And so what should I put down as the mass of calcium? Should I use 40.078? No. What I'm going to do is I'm going to use 40.08. This is a time saver. What are the units here? U per atom or I have two choices here. You know, the two units I could use are U per atom or grams per mole of atoms. Those are the two units. So, but I'm going to leave the units off because I can pick whatever one I want. Yeah. And then I have two chlorines. The chlorines are pretty common too, so I have that number memorized, 35.45. And so two of those will make 70.90 plus the 40.08. And that's going to give me 8. I'm sorry? Oh, fluorine I don't have memorized. Sorry. Actually, I do have it memorized because fluorine, fluorine's special. What's special about fluorine? Does anybody recall something special about fluorine? Fluorine only has one isotope. And so that means every single fluorine atom is going to weigh 18.998 U, which means the average is going to be 18.998 U. So all the atoms are going to weigh the same. Whereas chlorine has two different isotopes, so none of them weigh 35.45. And so fluorine, what number are you going to use here? Two fluorines, two at what? It says 18.998. Am I going to write 18.998? No, I'm going to write 19.00. And so 19 is going to be 38.00. So this is going to be 78.08. All right. So when I look at calcium fluoride, calcium fluoride is going to be 78.08 U per what? U per calcium fluoride formula unit. That would be 1 calcium and 2 fluorides. Or it's going to be 78.08 grams per mole of calcium fluoride units. Let's see what the book did here. Oh, actually the same, you know. That's good. So we don't have to do any rounding here. 78.08. All right, let's take a look at moles of various substances here. So we can figure out how much a mole of iron weighs. You know, a single iron atom weighs 58.85 U, a single iron atom on average, right? And therefore, a mole of iron atoms would weigh 55.85 grams. And so all they did was they weighed out 55.85 grams here, and then they can tell you how many iron atoms are in there. 602 million trillion. A single aluminum weighs 26.98 U. A mole of aluminum atoms weighs 26.98 grams. And so again, they just weighed out 26.98 grams. How many aluminum atoms are there? 602 million trillion. Mercury is a heavy atom. A single mercury atom weighs 200.6 U per atom. A mole of mercury atoms weighs 200.6 grams. And so this would be 200.6 grams of mercury, and that would have 602 million trillion. Nitrogen, this would be 28.02 U per molecule, or 28.02 grams per mole of molecules. And so in here, there are going to be 602 million trillion nitrogen molecules. And then we have sodium, we have copper. We go over here, remember this one, the copper 2 sulfate pentahydrate? In this one, a single formula unit would weigh 249.70 U. A mole of these formula units would weigh 249.70 grams. Now, if I have a mole of these formula units, 1 mole of formula units, in that mole of formula units, how many moles of water are there? So if I have one of these, how many of waters do I have? One whole thing, I'm going to have 5 waters. Does that make sense? And so 5 waters, well, that's about 18, it's rounded up to 20, so that's about 100 grams. Out of this mass, about 100 grams of that mass is water being sucked into the crystals here, the hydrate. We could get rid of that 100 grams pretty easily. How could we get rid of that 100 grams of mass? We throw it in the oven. You throw it in the oven, this is going to dry up. You lost 100 grams through dehydration. All right, is this molecules? Water is molecules, but this is an ionic lattice. And so we'd say formula units here. How about this? Mercury 2 oxide. Does that form molecules? Or, no, this would be formula units. How about water? Molecules. How about oxalic acid? Now acids are tricky because we had HCl, and we actually named HCl two different ways. We named HCl as the acid, and we named HCl as the gas. In the gas, we called it hydrogen chloride. In the acid, we called it hydrochloric acid. Yeah. In the gas phase, it turns out that HCl is kind of weird. It's a cross between molecules having HCl molecules floating around versus ions having H plus and Cl minus ions. When we dissolve HCl in water, it breaks apart into ions, the H plus and the Cl minus. But when it's in the gas phase, it's together as a molecule. And so this is why we have two different names for some things, because whereas, that's pure HCl, which is a gas. Pure oxalic acid is a solid. And pure oxalic acid, we only use one name for it, whether it's dissolved in water or in the pure form. It's just called oxalic acid. We would not call this hydrogen oxalate. It would be another name for this. It's just uncommon. And so this is oxalic acid. This would be 602 million trillion oxalic acid molecules. And over here we have oxalic acid dihydrate. You can see that it picks up some water. How much water does it pick up? It picks up 36 grams of water. Dihydrate per mole. Did the volume increase much? The volume, it might expand, it might not, because water molecules are quite small. If you think if the water molecules squeeze between the oxalic acid molecules, it expands it. It doesn't always happen that way. Sometimes it fits into these void spaces that would be present regardless if there's water or no water in them. Okay, let's do this one. You're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of compound do you measure out? And so these are the typical things that we're going to see here. Let me skip this slide for right now. I'm going to show you. Typical things that we see are these types of conversions here. So for example, we can go from the number to moles. Like 6 units would be half a dozen. Or 3 times 10 to the 23rd would be half a mole. And then from moles to grams. We use the conversion factors, Avogadro's number here, and MM stands for molar mass. So this is units to moles to grams conversion. Or we can do grams to moles conversion. Grams to moles using molar mass and then Avogadro's. We got to flip it one way or the other. And so let's take a look at this particular problem here, the previous problem. Let's see. So we're going to go from moles to grams here. So what do we need? One of the things we typically need is molar mass. So barium chloride, what's the formula for barium chloride? BaCl2. That's correct. That's good. All right, so we got to figure out barium. What is the average barium weight? So we'll go back to the periodic table. Take a look. 137.3. Except I wouldn't leave it like that. I call it 137.3. I wouldn't do sub 2. I do it 137.33. We don't have to do a sub 2 because we're giving it to 6 sig figs. We're just rounding it to fewer. I could do a sub 2. But this is one of those things where we're going to do intermediate round-off. I told you I don't like intermediate round-offs, except we're going to do intermediate round-offs when we calculate masses, whether molar masses or in this case, formula masses. And then we're going to have 2 chlorines. 2 chlorines is 2 times 35.45, which is going to be 70.90, calculated earlier. So this is 312. 2823. 2823. So let's go back to the original problem here. So the first thing we're going to do is calculate the molar mass. Take a look what they did here. Now they're after 4 sig figs now. If they're after 4 sig figs, they rounded this to the nearest 10th, but we don't have to do that. There's no damage in putting 5 sig figs at all. In fact, it's better, minimizing round off error. So do decimal places. Just leave it. And so they did 4 sig figs for barium, 4 sig figs for chlorines, and then they end up rounding it to the nearest 10. Just give them 4 sig figs. I have 5 sig figs, which is fine. 28.23. All right, then what we have is 0.0360 moles. So 0.0360 moles is how many sig figs? That's 3 sig figs. So we would prefer at least 4 sig figs in our conversion. We have 5 in this case. So what is it? It's going to be 208.23 grams of barium chloride per mole of barium chloride. Now this is something that often happens. It gets tiring writing this. This is actually moles of barium chloride molecules or moles of barium chloride formula units. And so it gets tiring writing formula units like this. Right? And so a lot of times people leave that off and just call them moles of barium chloride, but really what they're talking about is moles of barium chloride formula units. Okay, let's go on here. And so what we do is we cancel out the moles of barium chloride formula units and we're left with grams of barium chloride. So that gives us 7.50. They're back to rounding it. We want to know what the other digit is. 7.50 grams of barium chloride. There's some more. Let's do this one. And then we'll end it. We'll end it with this slide. 3.2 times 10 to the 24th molecules of sulfur tetrafluoride. So sulfur tetrafluoride, what is that? Molecular or ionic lattice, covalent lattice? What is that? Molecular. It's molecular. And the formula? S4. Okay, so let's take a look at sulfur first. So if we go to sulfur here, all right, what is sulfur? 32.07. Again, we're going to round off. It's okay because we're going to just introduce, and typically that's what's done. People will round off. Fluorine, we already saw before, is 19. We have 4 of those. So 4 fluorine, 4 at 19.00. Add those up. When we add those up, we should get what they got, except one thing here. Actually, 2 things. 2 things that I don't like. I want to be consistent here. So if we're going to round it to 2 decimals, we better round it. So they didn't round this properly. This should have been rounded to 0.07. And the second thing is they're not paying attention to the sig figs. This should be 4 sig figs. And the third thing, actually 3 things, is when we do this, this is an addition. When we do addition, we have to line up the decimal places. So we should do this vertically. We shouldn't do it horizontally like this. And so basically, figure it out. Yeah. Comes out to that. But I'm out of time, so I'm going to stop here.